Well, class, let's begin. Settle down, calm down, don't be so excited.
Today we'll be starting section 4.9, scientific notation. That's right, scientific notation. The material that you will learn today will be useful in other classes, such as chemistry and maybe even your physics class. And you will certainly see it in other math classes. So please buckle in and let's get started. First, we need to go over what is scientific notation, and here's a definition for you. Scientific notation, this is a description of how you write using scientific notation. Scientific notation is written as the product of two factors, okay? The product of two factors. Remember, product means multiplication problem, okay? So we have two factors, basically meaning two numbers. One of the numbers, the first number, is going to be greater than or equal to 1 and less than 10. What I mean by that is, basically you're talking about a number that is either equal to 1 or greater than 1, but it can't be bigger than 10. So you could have a number like 2 or 3 or 7.8 or 5.3235. You know, all of those are numbers that are bigger than 1 but less than 10, so they meet the requirements. The second number in our multiplication problem that we're going to be doing is a power of 10, meaning it's going to be 10 and it's going to have an exponent with it. This happens every time. So I'll give you an example of what this means. So here we have a number. So the first number we pick, you can just make up a scientific notation number right now based off this information. Like I said, pick any number, the first number that meets the requirements. So it needs to be bigger than 1 or it could equal 1, but it has to be less than 10. It cannot equal 10. So we could pick something like 3. We could say 3. And now this is a multiplication problem, so we need to put times. Now, scientific notation typically is written with the X times symbol, okay? I like to make mine float up a little above so we know it's not an X, okay? Then the second number we have is a power of 10. So you could put 10 and you could put it to like the third power, okay? So here we have 3 times 10 to the third power. Now you could work this out or type this in a calculator or whatever and get what this equals. But what this equals is 3,000, okay? And you'll notice the number of zeros matches this. That in this problem happens to be more of a coincidence. It's not a rule that the number of zeros has to match that number. In fact, there are several situations where it will not match that number. We're going to go over more of that in just a little bit. Just know that it does not have to match that number. Now some of you are thinking like, okay, this is just weird. Why write like this? Well, can some of you think of a practical reason to write like this? Well, let me give you an example. Would any of y'all want to have to write this number out a bunch of times? Let's say you had the number 8. There you go. Put an 8 right here, and this is going to be the number. Okay, anyone have to write that number down a bunch of times? It's pretty long, gets complicated. It's not even a really big number in the terms of sciencey numbers go. There's so many numbers that are so much bigger than that. But here we have an 8 with tons of zeros behind it. Well, this is equal to, this is what we call standard form. It's the normal way we write. This is equal to, in scientific notation, it's got an 8 times a 10. You're always going to have times 10 whenever you write in scientific notation. And in this case, the exponent is going to match the zeros, but it doesn't always happen. I'm just going to count the zeros real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have put a 13 right here. And you might be thinking, wait, why are you counting the zeros? Well, I'm not really counting the zeros. What you do is you actually start the back and you count all the numbers. You count all the numbers, regardless of whether there's a zero or not. You count all the numbers except the first one, okay? You don't count the first number, okay? And that tells you what you're going to put there. So let's take a look at some examples now, okay? We're told to write in scientific notation, and here's the one we're given. We're given this number. So what you do is you're going to put down your 2 times 10. And count all the numbers except the first one. So you could start at the first one, then just go back behind it and go 1, 2, 3, 4, 5. And you put it to the 5th power, okay? Now, next, you go over to this number, and I just copy it down like this. Now, this is the interesting part here, because remember, you don't just put down a 2. That's not gonna fly here. I need to include all of the non-zero digits. Okay, I need to include all these non-zero digits. You don't include these zeros in here, but I need to include them. But is there a way that I can include these numbers in the order they're written, but still have a number that is less than 10? I don't want to write down 257, but is there a way I can still include those? Well, there is. Maybe some of you remember this, but you put a decimal right here, 57. So you have 2.57 times 10. What's the power? Power is not 6. A lot of students go, oh, it's 6. That's how many zeros there are. But I've told you several times already in this short little video that you don't count the zeros. You count all the numbers past the first one. So you go 1, 2, 3, 4, 5, 6, 7, 8. So it's raised to the 8th power, and you're done. That's it. Here's some other examples. Math 7 has gone over some of this stuff already, but they've not seen examples like this yet. You're in pre-algebra, you get to see these fun examples. I want you to notice something, that these numbers are large, while these numbers are actually super small. Even though they got a lot of digits in them, they are super minuscule, tiny little numbers, and they're so adorable. Anyways, I know, like all of my scientific notation problems, I'm going to have a times 10 right there. I don't know what the power is, but I'm going to have a times 10. Now, you've got some numbers here. You've got a 7 and a 6. You need to write them in that order over here, okay? A 7 and a 6, okay? I have a 7 and a 6. The question is, how do I... But first I got to take care of one thing. 76 cannot be written there. You cannot leave that as a 76. What? But I thought, no, you cannot leave that as a 76. Okay? What you need to do is you need to put the decimal between them. Now that meets the requirements. Remember, we need a number that has to be less than 10. So that's less than 10. 7.6 is less than 10. So we know we have 7.6 times 10. Well, here's what you're going to do. To know what the number is up here, you're going to have to move the decimal back until you get it. So like, see our decimals here? We need the decimal to be here. So how many times did you move the decimal? You would do 1, 2, 3, 4, 5. So we get a 5 right here, but there's just a problem. If I put a 5 right here, this is going to change this into a very large number. Because if you type this on a calculator, you got 10 to the 5th power times that. That's going to become like a very big number, like in the thousands or tens of thousands, okay? So that's not what we want here, okay? That's not what we want at all. So what do we need to do about it? What do we do? What we're going to do is we're going to put a -5 up here. That -5 tells us that this was a decimal. Like we can work this out, and we'll see this more in class. But if you've got a decimal like this, and you have to move backwards, you're going to get a negative right there, okay? So these large numbers end up with the positive exponents, while these tiny numbers end up with the negative exponents. So over here, once again, what do we have? We got a 3 and a 5. So we put our 3 and our 5. Can I leave it like that? Nope. Got to put the decimal times, what I always times it by? 10. What's the power? Well, you have to move the decimal back. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 to get it between the 3 and the 5. So 15. Am I done if I just put it like that? No, because remember this is a small number. We had to move the decimal back that way. So we have to make it a negative 15. Okay? There you go. Write in standard form. Standard form is like these numbers right here, while this is scientific notation. So it gives us a number in scientific notation. Can we write it in standard form? Okay, so here's the most helpful thing to do when you're working these ones. just take this number and copy it down. Okay? It says it's to the 5th power. Take your pencil and place it right where the decimal is. Right there. Boom. See that? Sorry, my hand was blocking it. See that? Put my pencil right where that decimal is. Boom. And you are now going to move, if it's positive, you're going to, like on the number line, you're going to move in the positive direction. Okay? This works when you're going from scientific notation to standard form. So you're going to move in the positive direction. 1, 2, 3, 4, 5, and fill in your blank spaces. So you went from having a 2.9 times 10 to the 5th to a 290,000. Okay? Once again, an example. Copy it down. And then you're going to move the decimal over 10 times. Why 10? Because it's to the 10th power. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you get 0, 0, 0, 0, 0, 0, 0, 0. Okay? And 1, 2, 3, 4, 5, 6, 7, 8. Yeah, yep, that's all correct now. There you go. Let's do last two examples here. Last two examples. Here we have 4 times 10 to the negative 3rd. Well, you're going to put your 4 down. And remember I told you to put your pencil on the decimal, but you don't see a decimal. Like, oh no, where'd it go? Where's the decimal? I can't find it. It's right there. It's invisible. It's always behind the last number if you're looking at whole numbers, okay? So here we have to move the decimal towards the negative, like on the number line. So we move it forward. It's 1, 2, 3. So you put 0, 0, decimal. To put it over to the side, I'm going to put decimal 0, 0, 4. That's what that would have equaled, okay? So next we copy this down. We get a 9.32. We move the decimal in the other direction negative 8 times, so you get 1, 2, 3, 4, 5, 6, 7, 8. So we have 1. There you go. So this was equal to 0.00000000932. Okay? And that's how you work these problems. I'm pretty sure that you're going to have some questions on some of this stuff, but we will go over this more in class, and I'll explain some of these things in far more detail in the class. You just need to have gotten we've already kind of jumped in, and we'll cover how to swim in the classroom. All right, see you then. Bye.